So it's joint work with Mihir, Bellare, and Sriram, Keelveedhi. So this work explores an alternative to indifferentiability from a random oracle. So let me begin by recalling the random oracle model. So in the random oracle model, every party is given access to a box that gives random answers for each query. So answers of the box are consistent, meaning that if you twice ask the same query, then you will receive the same answer. So I call this variable input length random oracle model because the random oracle is willing to digest input of any length. So while this model is widely used in practice, it also received strong criticism. So on the theoretical side, a provably secure scheme in the ROM may be trivially insecure when the random oracle is instantiated by a concrete hash. On the practical side, there are structure exploiting attacks for real cryptographic hash function, such as the extension attack for the Merkle-Damgard structure. To mitigate the structure exploiting attack, Coren, Dodis, Molino, and Punilla suggested that we should move to the fixed input length random oracle model. So this model assumes only the presence of an ideal compression function. So one would give proof in the variable input length ROM as usual, but then substitute the big RO by an algorithm, which we call a domain extender, that has oracle access to small RO. In this kind of paradigm, we would need a definition, call it X, so that if the domain extender satisfies X, then we can safely use the domain extender to replace the random oracle in many schemes, and hopefully for all schemes. So current leading choice for X is the indifferentiability notion of Brenner, Mauer, Brenner, and Holenstein. So why indifferentiability works well in some setting, it also has some drawbacks. So first, as pointed out by Ristenpath, Sriram, and Sriram, then indifferentiability cannot guarantee security in a setting that we call multi-stage games. And even worse, you cannot generalize it to deal with all games. So another limitation is that existing indifferentiability constructions, say the Merkle-Damgard variance or the Spence construction, are largely sequential. So you cannot exploit the parallelism in modern multi-core machines. So given this situation, it's desirable to find an alternative for the definition X so that it can handle many multi-state games and it can have fully parallelizable construction. So we posit that a natural way to circumvent the multi-state insecurity is to make the definition X itself multi-stage. So the candidate for X that we are suggesting is our notion UCE in the prior work, which is indeed multi-stage. So UCE is not a single definition. It's actually a class of definitions for key hash functions. And in the prior work, we show that UCE can be used for several multi-state games, including the canonical counterexample for the failure of indifferentiability. As an added plus, UCE-based groups are even often simpler than ROM-based counterparts. And we also show how to build a UCE secure compression function in the ROM. You simply concatenate the key in the input, and you hash it. So today, we'll build UCE domain extenders in both the ROM and the standard model. So this, assuming that UCE secure compression function exists. So our first construction is generic, turning any indifferentiability construction to a UCE domain extender. So this shows an interesting relation between UCE and indifferentiability. So indifferentiability itself cannot directly handle multi-state games, but can be used in a black box way to meet a particular multi-state security notion, namely UCE. But the performance of this construction is tied to that of the underlying indifferentiability construction. We therefore propose another method that is fully parallelizable. Our instantiation using SHA for the random oracle can reach the peak speed of 0.4 cycle per byte 24 times faster than SHA itself. So before we proceed to the actual constructions, let me recall the UCE definitions. So here we have a source S that interacts with an oracle hash. For each of the query, the oracle either gives the actual hash output or a random string, depending on the challenge bit. So after a while, the source stops interrogating the oracle and sends a linkage to a distinguisher D. The distinguisher is given the actual key and then has to guess the challenge bits. So it's similar to the PIF notion, but here you give the key to the adversary, and consequently, you have to split it into S and D. So to avoid trio attacks, we need to place some restriction on the source, and each kind of restriction gives rise to a UCE variant. So a natural way to restrict a source is to make its queries unpredictable. So we would send the leakage to our friend, a predictor P. So after inspecting the leakage, P will output a set Q prime. It wins if Q prime can hit one of the source's query. And we say that the source is computationally unpredictable if the prediction advantage is negligible for all polytime predictors, and S is statistically unpredictable if the advantage is negligible for all, including computationally unbounded predictors. So this leads to two UCE variants, namely UCE cup and UCE soup. So here I stress that the prediction game doesn't involve the hash H at all. The source is always given access to a random oracle in the prediction game. So what I've seen so far are standard model definitions, but we can easily lift them up to a ROM-based notions by giving every party access to RO. So there's another natural way to restrict a source that we call recess security. So informally, it's fine if the source leaks some of the queries as long as the leakage contains no information of the oracle answers on those queries. And this leads to two other UCE variants, UCE CIS and UCE SIS. So now let's have a bird's eye view on the UCE extenders. So the first extender is based on an indifferentiability construction and can be used for UCE CIS or UCE SIS. These notions are the strongest in the UCE hierarchies, so you can use them for a dozen of applications in our prior work. So in the very next talk, you will see that UCE CIS is not possible in the standard model. So the standard model result for this construction applies only for UCE SIS, which is not subjected to attack. Another related result is Mitterberg's recent work that if you have an iterative indifferentiability construction and you use the key as a prefix, then you have a UCE secure hash in the ROM. But compared to our work, then Mitterberg's result can only handle a class of indifferentiability construction, and it can only work in the ROM. So our second extender is essentially the Carter-Webmin paradigm based on an almost universal hash. And it's a domain standard for UCE soup. We then build a very fast universal hash whose speed is about 0.4 seconds per byte. The intended applications are key derivation, message locks encryption, storage auditing, or oblivious transfer extension. So now let me describe the extenders in more details. So recall that indifferentiability operates on keyless compression functions. So the idea for the first extender is simple. You just key them. We therefore name it keyed indiff. So here's a canonical example for an indifferentiability construction. You use the Merkle-Darmstadt structure, and then you truncate the outputs. When you apply key indiff on this, then you just replace the keyless compression function by a keyed one. To realize this from share, then you mingle the key with the input, and you hash the mixed string. So this is the domain extender for UCCIS or UCSIS. The theorem statement is congruent with the good security bounds. Now let me move to the second extender. It's based on a universal hash. So conventionally, a hash is universal if the collision probability is small when you hash two distinct points. But when we move to an infinite domain, then you need to generalize that, because otherwise the probability is just 1. So we insert the bound on the string length, and the collision advantage is defined based on the number of queries and the total query size. So armed with these new notions, we just construct the second extender. It's based on the Carter-Webmin paradigm. So just apply the universal hash and then the compression function. So we therefore name it AU then hash. So this is a domain extender for UC soup, but the concrete power is not as good as that of the key indiff extender. So square root here may prompt you with a lot of questions. So why does it appear? Is it an artifact of analysis, or can we improve it? So recall that we demanded the input X to be unpredictable, but what matters here is the image of X under the universal hash, because that's what is fed into the compression function. So by the generalized leftover hash lemma of product at all, and there's a square root degradation in the unpredictability when you apply a universal hash, and this formula is tight. So actually there's no hope to improve the AU then hash bound. To ensure the usability of a AU then hash extender, that we aim to build very fast AU hash with small collision advantage. So we first did examine the tool. We will use a polynomial-based hash from F poly. It's just a variant of the classic Carter-Webmin construction, but can operate in any input length. The collision bound is pretty good, but it's quite slow for our purpose, because we aim to build share handsomely. We need another tool called AES4. It's the 4-round variant of AES. And I stress that we are not making any assumption on AES. It's based on a result in the cryptanalysis literature by Kelly and Sui that AES4 is an almost XOR universal hash if the subkeys are chosen independently. So the constant in the AXE formula is a little bit large, and we have to be mindful about that because there's a dangling square root on top of our collision advantage. This hash is really fast, but it can only operate in 128-bit strings. So we keep with these tools. We all have FAS4 that is fast and can operate in any input length. The collision advantage is pretty good, even under the square root. So it's just a birthday bound advantage because the big constant is associated with a small term. The key material is rather large, 672 bytes, but I think it's fine because the key is eventually released to the distinguisher. So it just functions as a public parameter. So let me proceed to actual construction. So the main component is a hash F fast. You need to run it twice with independent keys. The reason for this kind of doubling is to neutralize the negative effect of the square root. So when we zoom in the hash F fast, you will see that it just partitions the input into chunks X of 32 blocks. The last two chunks may be fragmentary. You then send the X chunk to be processed by a tree hash before we use the polynomial-based hash to digest the rest. So essentially, you use AES4 to string the input by a factor of 32, and then use F-poly to hash it. And here's a close-up view of the tree hash. So the picture illustrates a case that the input is 4 blocks, but it may go up to 32 blocks. So the depth of the tree may be at most 5. And at each layer, you use independent keys. So we run experiments to measure our speed of our hash with a share. So even in a sequential setting, that we are about 5.5 times faster than share. And if you have plenty of parallelism, then the speed up may go up to 24. So the take-home lesson is that UCE doesn't replace indifferentiability because it cannot handle all single-stage games. But UCE is a very good complement to indifferentiability. If your scheme enjoys a UCE-based proof, then there's no hidden multi-stage subtlety, and you will have a very fast instantiation. That's it. Thank you.